Hello everyone. In this video we are going to discuss Dining Philosopher problem of process synchronization. First we will discuss what is the problem all about and then we will look into the code details. So to begin with, we have 5 philosophers sitting on a round table like this. Each philosopher has his own rice bowl, but there are only 5 chopsticks. Each philosopher needs 2 chopsticks, so we need totally 10 chopsticks, but available are only 5. So there's a scarcity of chopsticks. Thus, Dining Philosopher problem represents a set of large problems wherein the number of resources available are less than the number of required resources. So coming back to the problem of philosopher, so each philosopher will be in one of these three states. So initially he'll be in thinking states. One, he's hungry, he transits to hungry state. He'll try to pick the 2 chopsticks, and once the chopsticks are available, he'll transit to eating state. And once eating state is done, he'll transit back to thinking state. Now the synchronization problem here is all the philosophers should be able to eat while avoiding the deadlock and starvation problem. So how the deadlock problem occurs here is, suppose each of the philosopher has the left chopstick and tries to grab the right chopstick which is with his neighbor. So this philosopher has this right chopstick and is waiting for the right chopstick. Similarly, this philosopher has this chopstick waiting for this chopstick. This philosopher has this chopstick and waiting for this. Similarly, this has this, waits for this. Similarly, this philosopher has this and he waits for this chopstick which is with the philosopher 1. Thus, each philosopher is waiting for other philosopher to release the chopstick. So, leading to a deadlock situation. And the starvation, for example, this philosopher is hungry, and whenever he is trying to grab the chopstick, either one or both of the neighbors are eating, and as a result this philosopher might not get a chance to eat. Now we'll look into the code details. So here we are including the header files pthread.h. So we are creating one thread for each philosopher, and then semaphore.h for semaphores and stdio.h. So here we have a set of constants defined here. N is for the number of philosophers, and we have constants thinking, hungry and eating to represent the philosopher states. The left and right constants here are interesting. So for given philosopher number phnum, left represents the number of the philosopher on his left side, and right will represent the number of the philosopher on his right side. For example, if the philosopher for the philosopher number 1, his left philosopher number will be 1 plus 4, 5 mod 5, 0. So his left philosopher number will be 0, and his right philosopher number 1 plus 1, 2 mod 5, 2. So for the philosopher number 1, his left philosopher number will be 0 and his right philosopher number will be 2. Here we have 2 integer variables, state representing the state of each of the philosopher and fill representing the philosopher number. Now important, we have 2 semaphores here, mutex and s. So mutex semaphore is, the purpose of the mutex semaphore is to ensure that the function calls by the semaphores are synchronized. And the purpose of s is the chopstick. So semaphore s represents the chopstick here. So we have 5 chopsticks. So S we have 5 semaphores representing each chopstick. Now we'll look into the main function. So here in the main we are creating an array thread of n. So of type pthread underscore t representing the thread ID, and then we are initializing the mutex semaphore. It's a binary semaphore. We are initializing it to 1. The third argument represents the initialized value. The middle argument 0 represents tells us that this semaphore is for the threads and not for the processes. If the semaphore is used between the processes, the middle value should be 1. Next, we are initializing the semaphores for the chopstick. You can see here the chopstick semaphores are initialized to 0, indicating that the chopstick is initially unavailable. The chopsticks will be available only when certain conditions are satisfied. And next, in this for loop, we are creating 5 threads. You can see it's running from 0 to n, and the first argument to pthread underscore create stores the thread ID, and each thread is going to execute a philosopher function, and the philosopher number we are passing as an argument to this philosopher function. And once the thread is created, we are putting the philosopher in thinking state, hence it's print as philosopher %t is thinking. Once all the threads are created, this main thread will wait for the all the threads to complete their execution by calling pthread_join. Now let us look into this philosopher function. So in this philosopher function, you can see that there's an infinite execution of while loop. Okay, each philosopher infinitely executes a while loop. In that, inside the while loop, if you see, there are two functions that the philosopher is calling: take fork function and put fork function. Take fork function will try to grab the chopstick. The philosopher will try to grab the chopstick and perform the eat operation. Once it's done with eating, it will put the fork by calling put fork function. Let's look into this take fork and put fork function. So the take fork function is here. It's taking the philosopher number as an argument. As I told you, the purpose of mutex is to ensure that the calls to the function is synchronized between the processes. Hence, at the beginning of this function, you can see the process is calling sem_wait mutex, so that no other process can call this function at the same time. So if one process is executing take fork, other process should wait to complete. So once the function is logged here, you are changing the process state to hungry. And then you're printing the process is hungry now. Now it's calling a function test. This test is very important and very interesting. We'll look into it. And once the test function is done with the execution, you're calling sempost mutex, so that if other philosophers, they want to execute the test function, they can go ahead. So basically this semwait mutex and sempost mutex are guarding our test function. The test call to test function is synchronized between the processes. We'll go to the test function, and then later on we will continue with the take fork function. So the test function is very interesting here. As the name itself says, this function is going to test if the process can eat. So you can see here, it's taking the philosopher number as an argument. It's going to check if the state of the philosopher is hungry, right? That particular philosopher is equal to hungry, and the state of left philosopher is not eating, and the state of right philosopher is not eating, meaning that the process is hungry while its neighbor, none of its neighbor, left neighbor and right neighbor, are not in eating state. What happens if they are in eating state? The chopsticks will not be available. If they are not in eating state, it means that his left and right, both the chopsticks are available, right? So if all these three conditions are satisfied, that is, the philosopher is hungry, his left one is not eating, his right one is not eating, he'll enter this if. He changes his state to eating, right? And he prints philosopher %t takes fork %t and %t, and philosopher is eating, right? And once he's done with eating, he'll call sempost of the semaphore S. As you can see, the semaphore which was with this philosopher is now released. It is released in the sense its neighbor can go ahead and take the chopstick if they want to. I mean, if they are waiting for that chopstick, they'll be released. The chopstick will be released, and they'll come out of their corresponding wait function. So very simple here. The test function checks if the function, the processor is hungry, its left and right are not eating. It will change its state to eating, and then once it's done, it's eating. It is calling sempost of the that particular semaphore, so that any other process which is waiting for that chopstick will be can continue its wait. Suppose if the process is hungry and this two conditions or one of these conditions are not true, then the process will return back without getting into the if to the take fork function. That is, if this if statement is not executed, one of its neighbor is eating probably, then the chopsticks are not available. So the process returns unsuccessfully back to the take fork function, right? So you can see here, after the test function, if the process is returning unsuccessfully, it's calling sem_wait of semaphore. That will make sure that the process waits for the chopstick, right? It waits. The chopstick is not available, hence it waits. Otherwise, also, even if he has completed its eating operation, then also calling semwait will set it back to 0, which has no effect. right? So this is about take fork function. Let's look into the put fork function. So the put fork function, here it takes the philosopher number as an argument, and then it's calling some wait underscore mutex, right, to make sure that this is executed one by one process at a time. Then it's calling some, then it's changing its state to thinking. It's printing the message philosopher %d is putting the fork, and then the philosopher is thinking. Now this is important here. See, the process has completed its eat operation, right? So now what it should do is, if one of its neighbor is, it should check if their neighbors are hungry and they are in waiting state. In that case, it will call test of left for test function for his left neighbor, and he calls test function for his right neighbor. So what is the purpose of these two, test left, test right, is, if at all, if their neighbor, see, this process is done with eating, right? So when this process was eating, probably his left neighbor might be hungry and waiting, right? So this test function will help the left neighbor to continue in case the process is waiting. Similarly, if the right function, right, it will help. The philosopher is going to help its left and right neighbor by calling test of left and test of right. So if they are hungry and they are waiting, they can this call will help them to proceed. If they are not hungry, if they are not waiting, then it has no effect, right? Finally, after executing test left and test right, it will call sem underscore sem post mutex. Completing this function put fork. So here in many places you can see we are calling sleep of 1, sleep of 0. That is because this program is executing in infinite loop, right? And we are creating 5 threads. In order to provide little of the output should be synchronized, right, on the screen. Hence we are calling sleep, so that we will be able to see the output properly and we are not missing anything. So that's the purpose of using the sleep function here. So that's it. We have seen. So the each philosopher calls philosopher function. In the philosopher function, you can see the philosopher is calling take fork and put fork function. We have seen what is take fork function. Take fork function basically calls test function, right? Take fork function basically calls the test function, right, within the wait mutex and some mutex and wait mutex. And then the test function, it checks if the philosopher is hungry and its neighbors are not eating. It will put it into eating state and releases the semaphore, right? And what put fork function does? Put fork function similarly simply changes the process state to thinking, and it calls test of left and test of right. Such a good philosopher it is. It is checking for its neighbors. We should appreciate that, right? So this is all about put fork function, right? So this is how the dining philosopher. So this is how the dining philosopher code runs. So you can see all the philosophers are initially in thinking state, then hungry state, and you can see philosopher 3 is taking fork 2 and 3. So what you need to observe in this output is 3 things. One is there is no deadlock, in the sense the code is executing. It's not stopping in between. If it is stopping in between, it means that there's a deadlock condition. Second thing is no starvation. All the philosophers should get a chance to execute. And third thing is no 2 neighboring philosophers are eating at the same time. Like say for example, if the philosopher 3 is eating, then its neighbor 2 and 4 should not be eating at the same time. So these are the 3 things you need to watch out in the output of a dining philosopher. So that's it. Thank you.